Okay, the second class of causal methods that I want to discuss still use this conditional independence assumption to achieve identification, but they introduce a quantity known as the propensity score for estimation, for estimation and identification. And this is a quantity that focuses directly on treatment assignment and on the factors that influence treatment assignment. So one way of illustrating this, where the propensity score fits into the whole picture, is to write the joint density of the variables in our causal model in this form here. So remember, when we introduced notation, we said we had a triple of data, y, d and x, and this is the joint density, which due to the chain rule from random variables we can write in this form here. Now the first element here, this is what the outcome regression models that we've just covered focus on. So the expectation of y given d and x, or in other words, outcome regression looks directly at the relationship between outcome and treatment conditional on the covariates. That's the point. The innovation underpinning the propensity score approach is to focus not on this first element per se, but on the second element. That is to shift the focus to the relationship between treatment assignment and covariates. So in doing that, in shifting the focus in that way, we're looking directly at the structure of confounding, and we're going to model it. We're going to assume a model for assignment to treatment given covariates, and we're going to use that model to form what's called propensity scores, provided in this definition here. So the propensity score is a scalar value. Actually, it's a probability. So it's a single number for unit I that measures the conditional probability of assignment to treatment given the confounding covariates. So for binary treatments, the propensity score is simply, and it's denoted pi, conditional probability of d given x. It's the probability of being treated given the vector of covariates that unit I has. And for multivalued continuous treatments, again denoted by pi, but this case for d equals small d, it's the probability of being assigned dose d given the vector of confounding covariates that unit I has. So the propensity score then, or the PS, is focusing directly on the relationship between treatment assignment and covariates, telling us how the latter, the confounders, determine the former, the treatment assignment. Now the question is, why is that useful? Well, an important feature of the propensity score is that it balances the distribution of covariates, and that property is described in this box here. So the treatment assignment and the covariates are independent given the propensity score, expressed here. Treatment assignment and covariates are independent if we condition on the propensity score. Now essentially all this is saying is that the covariate vector xi and the scalar quantity pi are exchangeable in the sense that they contain the same information, and they can both be used for conditional independence. And this balancing property follows simply because the propensity score is a function of x, function of the vector x, and so conditioning on x adds no additional information. I'll just show you how this looks in a DAG. This shows the balancing property via the propensity score. Conditioning on the propensity score, because the propensity score is entirely determined by x, essentially blocks that indirect path. So you see here, it blocks the path between x and d. That's what balancing achieves. So it puts this intermediate step here on the route from x to d. That's balancing. So balancing arises because the propensity score summarizes all the relevant information on confounding in a single value, and it therefore follows that the conditional independence assumption can be stated conditional on the propensity score rather than x. So given balancing, given that this property exists, we can kind of interchange these two quantities to obtain independence with d. Given that exists, then we can establish conditional independence on the scalar propensity score rather than the potentially high-dimensional covariate vector x. So this is conditional independence assumption, but we have replaced x, which is a vector, potentially high dimensional vector, with a propensity score, which is just a scalar value. Thus, if the conditional independence assumption holds on x, then it holds on the propensity score, and the propensity score effectively adjusts for confounding and can be used for causal identification. And again, you see that in the diag here. Rather than worry about the causal path from xd to y, we can now worry about the causal path that goes d via the propensity score to y. This being treated as a parent of both d and y, and in that case we don't have to worry about x. So conditioning on the propensity score is blocking that indirect path and forming a new path via this route here. Now the question is, why is that useful? And we'll turn to that in a minute when we come to look at estimation. First of all, I'll just show you that identification can indeed be achieved given the propensity score. Under conditional independence of the average potential outcome, under conditional independence, identification of the average potential outcome, μd, via the propensity score can be demonstrated as follows. So here we have our estimand here. We condition on x and we take expectation over x, so that's iterated expectations, that's just what we've seen before. Due to the conditional independence assumption, we can condition on x. Due to the balancing property of the propensity score, we can replace x with this vector here with the scalar value here. And therefore, once we have conditioned on the treatment assignment indicator, we can get back to the observed data. And therefore, the conditional independence assumption has been restated with observed data, and it's therefore identified as long as we can get a value of the propensity score. So given that identification can be achieved by using the propensity score, that means we can construct propensity score based estimators for average causal quantities. Now PSs are not observed, we have to calculate them by estimating the relationship between d and x, and we do that using a regression model. So propensity score analysis involves two steps. First of all, we have to estimate the propensity score, and then we use it in a model to estimate causal effects. And we would just do it through a simple regression. So for instance, in the binary case, we would estimate the propensity score via this kind of regression, being a logistic regression, say. In the multivalued or continuous case, g would be some other link function. And the estimated parameters of this model are plugged in to give us our estimated propensity score. That's how we compute the propensity scores themselves. So once we have our estimate of pi, estimated propensity score, we can use it to then go on and estimate causal quantities, average treatment effects, and average potential outcomes. But you might be wondering, why bother using the propensity score? Why not just use x itself? What's the advantage in having a propensity score? Well, the key advantage of the propensity score is this dimension reducing property it has. So propensity score means we no longer need to deal with and condition on a potentially high dimensional covariate vector. We can use a scalar value instead. And the fact that we've got a scalar value facilitates design and use of very effective flexible estimators that would be much more difficult to implement in a high dimensional setting. And we'll look at three of them here, three propensity score based estimators based on weighting, regression and matching. All of them are conditioning on the propensity score, they're just doing it in different ways, doing it through weighting, doing it within a regression model, or doing it through what's called matching. Okay, so let's look first at the first PS estimator. This is called inverse propensity score weighting, or IPW. And the idea underpinning IPW estimation is that we can estimate an average treatment effect, and it's justified by a law of large numbers using an expression such as this here. So it's the difference in the weighted sample or outcomes where they're weighted by the propensity score at level D, minus the weighted sample of observations for control groups weighted by the propensity score for treatment level D equals 0. That is treatment control. Now this is an average potential outcome or an estimate of the average potential outcome, an IPW estimate of it at treatment level D, and this is an estimate at treatment level 0. So it's really simple. We just weight outcomes by the relevant propensity score value and we take the difference. Let's just have a look at how weighting achieves identification of an average potential outcome, and it's shown in this slide here. So here we have an average of PS weighted outcomes. These are outcomes observed in the real data this time, so we're starting kind of the reverse way. Through the stable unit treatment value assumption, that the fundamental consistency property I discussed earlier, as long as we are talking about an indicator variable saying di received dose D, then we can replace yi with its potential outcome, because these two numerators are the same in this case. We can condition on x. We're allowed to do this via the conditional independence assumption. So that's what we've done there. We're conditioned on x and we've taken iterated expectations, and that's just the same quantity here. That's just an iterated expectation. Once we've conditioned on x, we'll write out the numerator in this form here. So expected value of treatment assignment given x, expected value times expected value response given x, and due to the balancing property of the propensity score itself conditioned on x, conditioning makes no difference, so we don't have to condition on x in the denominator. But this expression here is just a propensity score. That's the definition of a propensity score, so we can write it in this form here. The two propensity scores cancel out. It gives us this expression here, which gets us back to our average potential outcome. So yeah, just demonstrating how IPW lets us get to APOs. So the IPW principle then involves creation. Essentially, the way to look at it is by weighting, we're creating a pseudo sample that allows us to mimic what randomization would look like. So we know that under a random assignment, the probability of assignment to treatment is uniform in the sample. So the probability of assignment to treatment is always the same under a random assignment. There's no systematic tendency for some units to have a higher probability of receiving a given level of treatment than others. But in a non-randomized, in a confounded situation, that's not the case, because X determines assignment to the treatment, and the probability of assignment will differ depending on the vector of X that you have. So the principle that's simply being used here is, if we know how those baseline characteristics, the confounders, cause deviation from a uniform probability, then by simply weighting the units by those probabilities, we can get back to something that looks as good as random. So units that are, on account of their covariate vector, less likely to receive dose D get emphasized. Units that, because of their covariate vector, are more likely to receive dose D essentially get diluted through weighting. That's the principle that's being used. So that's IPW estimation. I'll quickly cover two other ways in which we can use the propensity score for estimation, and it's just one slide each. First, regression on the propensity score, or PSR. Since the CIA can be established conditional on the propensity score rather than on the vector X, then we can simply substitute propensity scores straight into a regression model that we used in the previous section on outcome regression. We can just replace X by the propensity score, and that will do the same job, because the CIA holds conditional on X. So we don't even need to do any more theory. We know that that must be the case. So adapting the outcome regression model discussed earlier, we take X out and we plug in our estimate of the propensity score. Remember, this has to be estimated in stage 1. And we can then estimate an average treatment effect for some dose using this expression here. So this is simply the fitted values of the regression model at dose d equals small d, with propensity score evaluated at d equals small d, minus the fitted values at d equals 0, with propensity score evaluated at d equals 0. So where gamma are parameters to be estimated from this regression model that approximates this conditional expectation, and alpha hat are the parameters of the propensity score estimation model that's been conducted in a prior step. So the logic underpinning PSR estimation simply follows from the identification property described in Theorem 2. That is this expression here. But why would we want to do it? Well, a key advantage, as we've said earlier, is that the propensity score is a scalar, and that allows flexible, or it makes it easier to use flexible high-order polynomial or semi-parametric models to be used. So it's a much simpler outcome regression model. We have only two covariates, d and the estimate of the propensity score, and that makes it much easier to implement flexible and significantly non-linear models, say with interactions. And then finally, the final propensity score method I want to discuss is propensity score matching. And I've included this approach here, this method of estimation here, because it's actually very popular. And if you look at the literature on causal inference, many applications, certainly for a number of years, were based on matching estimators. Now, in general, a matching estimator simply seeks to fit an algorithm that identifies units that are similar across covariates and then contrasts their outcomes by treatment status. Propensity score matching is a popular approach because the propensity score provides an ideal value on which to make the matching due to its balancing property. Because what the balancing property says in practical terms is that units with the same propensity score can be treated as directly comparable in Y, and exposure to the treatment can be regarded as random given the propensity score. So that's balancing. And essentially what we're saying is that once we've matched on a propensity score, once we've got units that have either identical or similar propensity scores, then essentially we've already conditioned on the propensity score, and so we can just compare the outcomes, and that's going to give us the treatment effect. And the matching estimator is really as simple as that. It uses the propensity score to match a small number of neighbours to approximate the unobserved outcome for a given unit. So it's a simple comparison of observed outcomes with averages over units that have the same propensity score. And the expression is shown here. So this is how we'd estimate an average treatment effect for a binary treatment, 1, 0 in this case. In this case, the values that we plug in are the value of the outcome we observe for some unit I. We don't observe the control because of the fundamental identification problem of causal inference, so instead we plug in an average for units that have the same propensity score as I. Simple as that. Average of neighbouring units with the same propensity score, and it can be shown that that actually provides a consistent estimate of the average treatment effect. Great, okay, last part of this section, I want to now bring together what we've learned about outcome regression and IPW via an example. This is an example that we're going to conduct via simulation rather than real world data. The reason being that we want to demonstrate our ability to estimate causal effects. So in order to do that, we have to set the data generating process essentially and show how confounding is causing a problem. Actually generate data that includes confounding. So we're going to continue with this speed cameras idea. So our objective is to quantify the effect of speed cameras on road traffic collisions. There's a causal inference problem because the assignment of speed cameras is confounded. They're allocated according to a set of criteria that are also relevant for our outcome. We have data at the link level, so for individual links in the network. The response is continuous. It's a road traffic collision rate. It's not just an integer, it's a rate. We've got a binary treatment presence of a speed camera or no speed camera. And we have a set of covariates represented by X that represent confounders. This is the data generating process. So you can see here that X is relevant for assignment to treatment, and it's also relevant for outcome, as is D. Therefore, we have confounding. These are the parameter values we've set in the simulation. We want to estimate the average treatment effect, and that's given by parameter tau, which equals -5. So that's the true causal effect that we want to estimate. And we're going to simulate the following models. First of all, we're going to simulate a correctly specified outcome regression model. So this is an outcome regression that includes both D and X, as it should. Secondly, we're going to simulate an incorrectly specified outcome regression model that excludes covariates X and therefore does not adjust for confounding. Next, we specify an IPW model based on a correctly specified propensity score, estimated using some logistic regression, say. And then we simulate, in number 4, an IPW model, but where the propensity score is incorrectly specified, in this case just randomly generated from a normal distribution. And finally, we're also going to use a naive model based on the difference in sample means that would give us a good answer did we have unconditional independence, but we don't due to the way the data generating process has been set up. So each simulation is based on 1,000 runs, so 1,000 Monte Carlo samples on generated data sets of size 1,000. Having run the simulation 1,000 times, we then look at the average estimate, essentially the expected value of the estimate. We look at the empirical variance, essentially the sampling distribution of the estimate, and we look at its mean squared error. So what did we find? The correctly specified outcome regression model that estimated this parameter provides a good approximation to the true value, so we're pretty close up here. When we fail to adjust for confounding, so when we don't include X in the model, we get a poor approximation to the true ATE with significant bias, as shown by the difference between empirical variance and MSE. We get this value here, so it's quite far away from the true value. The IPW estimator also does well. So propensity score, when it's correctly specified, gets us spot on, but actually this estimator has slightly higher variance. And that tends to be the case. That's a feature of weighting estimators, because weights that are either very high, when propensity scores are very close to 1 or very close to 0, that can create some instability. So it's got quite big variance, this estimator, but it does get us spot on in terms of the treatment effect. When the PS model is misspecified, as we have here, then we get just it's very, very far away. It just gives us a spurious answer, and it's very, very far away from the true answer with huge MSE. And similarly, the estimate based on sample means, actually very similar as you would expect at OR2. It doesn't adjust for confounding, and consequently it gives us a bad estimator with noticeably high bias.